we have problem number 8, and we are given a PV diagram where there are 3 steps in a 3-cycle heat engine. So it starts at point A, goes to point B, then goes to point C, and then back to A. So what we want to solve for is the change in thermal energy, Q and W, which is work, for each of the 3 steps, and then get the totals for all of them. And then from there we can compute the thermal efficiency of the heat engine. We were given a few bits of information. We know that CV is equal to 2.5 R, and then CP is equal to 3.5 times R. And we know that we're given that at step B to C is an isothermic expansion, and it's given to us that that happens at 800 degrees Kelvin. So the first thing of information we don't have is the number of moles, which is what we need to compute the whole thing. But we do know that at point B, we know that it is 300,000 pascals. All right, so we know that PV is equal to the number of moles times the R constant times temperature, and we know at point B, we know the pressure is 300,000 pascals. We know that the volume is 0.002 cubic meters. We don't know the moles, that's what we're trying to solve for. We know the constant is 8.31, which is R, and we are given that the isothermic expansion is at 800 degrees, which is when isothermic expansion begins, is at point B. So we do that math and we get the number of moles to be 0.009 moles. Another bit of information we need, but we don't have, is the temperature at point A. So that's the same equation, pressure times volume is equal to the number of moles times the constant, but now we don't know the temperature and we need to solve for that. So we did the algebra to get the temperature at about 200 degrees Kelvin. From there we could solve the rest of the equation. All right. So the first thing we're going to do is the process from A to B. We know that in A to B is a isobaric contraction starting at the pressure of 75,000 pascals. So we know that in a isobaric contraction, Q is equal to the number of moles times CV times the change in temperature. We got the change in temperature from the initial temperature from A to B, which is the difference is 600. We know the moles at 0.009, and we're given CV initially in the problem. And that will be equal to 113 joules. Now also in a isobaric contraction, there is no work done on the system, and we know that the change in thermal energy is equal to the sum of Q and W. Since W is 0, and we just solve for Q, in an isobaric contraction, change in thermal energy is simply equal to Q, which is 113 joules. Next, what we solved for was the process from C to A. C to A is the process which is isobaric, which means that the pressure remains constant. Now, in an isobaric contraction, the change in thermal energy always is equal to the number of moles times the CV constant times the change in temperature. We know that at point C, the initial temperature is 800 degrees Kelvin because it just went through a isothermal expansion. And so the change in temperature would be -600 from C to A. So it's 0.009 moles times 2.5 times 8.31 times negative 600, which gives you negative 113 joules as the total change in thermal energy for the process C to A. We know that Q in a isobaric process is the number of moles times Cp, which is a little different because in an isobaric contraction the pressure remains constant, and that is 3.5 R. R is 8.31, is that constant we know, and the change in temperature still is negative 600. And to do the algebra, we get negative 158 joules. Now, work is simply just change in thermal energy minus Q. And we took those two numbers, and that is equal to positive 45 joules. Next is the process of B to C. That one is a little trickier. It is the isothermal expansion. In an isothermal expansion, there is no change in thermal energy, which means that Q and W are opposite of each other. So if Q is positive, W is negative. Now, work in a isothermal expansion is equal to the negative integral from initial volume to final volume, and the integral of the number of moles times the constant R times the temperature throughout the process over V times dV. And to do that integral, we get negative nRT times the log of final volume over initial volume, and we just plug those numbers in. Negative 0.009 moles times 8.3, that constant, times 800 degrees Kelvin. And then 4 is simply just, we know that the volume at C is 800 cubic centimeters, and at A is 200 cubic centimeters. So that ratio is 4, so we do log 4, and we get it is equal to about negative 83.2 joules. Now Q is equal to negative W, which means that Q equals 83.2 joules. So now we've written out the totals for each of them. As we said, A to B, change in thermal energy is 113 joules. Q is 113 joules as well, and there is no work done on the system. B to C, we said is isothermal, so there is no change in thermal energy, which is 0 joules. And Q and W are equal, Q being 83.2 joules and W being negative 83.2 joules, which we just calculated for. And then the process of C to A, we calculated the change in thermal energy to be negative 113 joules, Q negative 158, and W is positive 45. Now the totals for the entire process, change in thermal energy is 0, which makes sense because we came back to our starting point. So net, there is no change in total change in thermal energy. We got a total of Q is 38.2 joules, and since change in thermal energy is the sum of Q and W, W must be negative 38.2 joules. Next, we calculated for the thermal efficiency of the heat engine, and that's just taking your total output of Q over your total input that got you your output. So that's 38.2, which is our total, and the sum of the inputs, which is 113 joules and 83.2 joules, and that ratio times 100 will give us a percentage of 19%. So the heat engine total is 19% efficient.